Hello. Now we come to the chapter 4, which is the last chapter in the series of theory of machines. The chapter 4 being vibrations. In this chapter, we will learn the definition of the vibrations, and we will learn about various categories of that. So the topics in this chapter are free vibrations, second is damped vibrations, then we have forced vibrations, under the category of force vibration, a subcategory of critical speeds of shaft, that is the topic listed in the Gates levels. So what is vibration? We will consider the definition of vibration. Vibration is nothing but kind of oscillation of a body about a equilibrium point. And the other required condition for vibration is that oscillating motion should be periodic. So the oscillating motion should repeat itself after a finite interval of time. So that finite interval of time of repetition of the periodic motion is called time period of the periodic motion. So every vibration has a time period associated with that. So a cycle, that means if a cycle is there, the vibration can be of any shape, but there is a cycle time period associated with that t, and the oscillations are about a mean point, like you can define a 0 point. So there are various examples of the vibration. The simplest example is of a simple pendulum. There the pendulum bob is displaced from the mean position, and then it keeps on oscillating about the mean position. So this is the mean position, and the bob oscillates to and fro. So this is an oscillatory motion, and the time period in an ideal system would be constant. So hence it is an example of vibration. Another example of vibration is a mass hanging from a spring. So in this case, if you the mass is having the spring is having certain extension by default due to the gravitational force exit, existing, and it will have some mean position at 0. But you displace the mass in the spring system by some displacement, let's say a amplitude, then the spring mass will go back due to the extension. Some potential energy will be stored in the spring, and it will pull the mass back, and the mass will overshoot its mean position, and it will go be somewhere there to the top. Then it will have compression. So and then compression potential energy will be there. It will push the bob back. It will come again to the bottom position and its most expanded position. So spring mass system, this is also example of a vibrating system. So in general, in a vibrating motion, conversion of energy takes place. Vibrating motion, conversion of energy takes place between the potential energy and the kinetic energy. Energy and kinetic energy. So if you see this example, the simple pendulum, in this case the potential energy PE is the gravitational energy. So due to the change in height of the bob, when it is moving from the mean position away, there is some finite distance h, and due to increase in height, and the gravitational energy increases, and then it has to come back to its mean position to uh, decrease the potential energy, and the potential energy becomes 0 at mean position. So in all vibrating system, the potential energy is normally 0, So there are various kind of potential energy. When you're talking about the potential energy associated with the vibration, that the potential energy will be zero at the mean position. At mean position. And what about the kinetic energy? The kinetic energy is maximum at the mean position. So a bob is almost stationary at the extreme position. So extreme position, the oscillating mass is stationary. So there is zero kinetic energy, and at mean position the potential energy will be zero because the system is always trying to get towards the mean position. So mean position is the position of where all potential energy will be converted into kinetic energy, and therefore the mean position is the position of maximum kinetic. So the basic requirement for any vibration to happen is that the system should be capable of storing potential energy. So this is the first requirement, and the second requirement is the more obvious one. That is, the system should be capable of motion. So that's how it will have a kinetic energy, capable of motion. So the motion can be of any kind. The motion can be linear also. The motion can be angular also. In both of the cases, the principles that we are going to derive for the vibrations will apply. So in a linear case, let's say the spring mass system. So you have a spring, you have a mass, and then the motion is linear. The oscillation is linear. For the torsional case, let's say a cantilever is there and a disc is attached to the cantilever, and then the disc is displaced from the mean position and then left to vibrate. So it will vibrate about its mean position due to the torsion in the shaft. So this is called a torsion pendulum. The equation that we derive will be same for whether you are considering a simple pendulum or you are considering the torsional motion, angular motion. Just in angular system, the counterparts of linear motion will be applicable, and basic theory will remain same, nothing much will change. Basic. So as you can see from these three systems, here the potential energy is the energy stored in spring, and the kinetic energy is the mass which is having a Ke, which is capable of motion. In this case, the potential energy is the torsion in the shaft. So because of that, the energy will be stored inside the mass in the form of strain. So the strain will try to come back into equilibrium position. And in the case of simple pendulum, the potential energy is the gravitational energy. Kinetic energy is the mass. So you require mass. So the system should be capable of motion, should have mass, and should be capable of storing potential energy. Then conversion from potential energy to kinetic energy will take place during vibration, during the whole of vibration. And since the total energy of the system should remain constant, so hence Pe plus Ke will be equal to constant. So if you draw a graph of Pe, when Pe drops, the Ke will rise, and when Pe rises, Ke will drop. So like that, the graph will be formed, and exchange of energy will keep on happening. If the system is lossless, there is no losses of energy, lossless, so this constant will not change, so it will remain constant. So hence the vibration will continue forever. There will be no damping of the mass forever. So this case is called free vibration without damping. There is a second case in which there are losses in system. So due to the friction or windage in the motors, there are energy losses. So in that case, the total energy of the system will not remain constant. So PE plus KE will decrease with time because the total energy is getting reduced by losses in time. So in this case, one case is damped oscillation. So the oscillation will damp out, or they will reduce in amplitude and die with time. So they will keep on reducing in amplitude. It looks somewhat like this. Initially there is some oscillation, then reduce and then become zero. So these are called damped oscillations. Damped oscillations. And the other case is that external energy is supplied. This is case 1. Case 2 is external is supplied, and this is a case of forced vibration. So in each vibration cycle you are inputting some energy to sustain the vibration. So in case of forced vibration, the oscillation will continue forever as long as the energy is supplied. So they will not damp out with time. We'll consider in detail these topics. The basic condition for existence of vibration is a presence of a equilibrium position. This is also called mean position. So in a vibration, system oscillates about the equilibrium position. So in the vibration we are talking about the displacement of an object varying with time. So the displacement will oscillate about the mean position. So whenever you are doing any calculation for analyzing any system in the vibration theory, the first requirement is to identify the mean position. So in the case of pendulum, it is pretty much straightforward. When it is at 0 degree of angular displacement, this is the mean position. Spring mass also, when it is not having any velocity, it is just static in space, this is the mean position. So as you can see in both of these examples, that the potential energy and kinetic energy both are 0 in undisturbed state. Undisturbed state. So undisturbed state is just the pendulum lying in a vertical direction. This is vertical direction, and the spring mass without any motion, just hanging, and there is some extension in the spring. So here the we are not talking about the actual gravitational force. There will be some gravitational energy associated with the spring, the pendulum bob. Also similarly, there will be some potential energy in the spring at the mean position also. So we are not talking about the static potential energy. We will be talking about the dynamic potential energy. When the vibration is happening, the increase and decrease in potential energy. That is what we are interested from the point of view of the vibrations chapter. So we are not talking about the absolute potential energy, but the relative potential energy. So hence, what is the method of finding the mean position? You can see that if all of the energy is extracted, all of the vibration energy is extracted from the system, zero vibration energy, then you will get the mean position. So what happens during oscillation? During oscillation, the system is perturbed from its initial state, from its mean position. Perturbed means it is disturbed and brought to some other position where the potential energy is not zero. There is an increase or decrease in the potential energy. So the relative potential energy becomes assume some value. So you have non-zero PE. So this is the disturbed state, disturbed or perturbed state. The perturbed is the better word for engineering application state. So in this case, the system has non-zero vibration energy. So this non-zero vibration energy will be in the form of potential energy at the extreme position. So at extreme, everything is potential energy completely, and then when you release the system, the PE converts to kinetic energy, and then the bob crosses mean position, goes on the other side. So the spring also overshoots the mean position due to inertia. So a vibrating mass overshoots the mean position due to inertia. That is also a required condition for vibration. That's why mass is needed, and then it gets PE on other side or of opposite nature, and the system then again tries to come back to the equilibrium position. So in a vibration, you should always remember that the system at any instant in time, at any position in time, the system is always trying to get back to mean position. When reaching the mean position, it is having some kinetic energy, it overshoots and reaches the other extreme position. But again, it tries to come back to the mean position. So this overshooting and reaching extreme position is what is called a vibration. The nature of oscillatory motion can be of any general graph. So there is no need that should be sinusoidal or something. The vibration. So on y-axis we are plotting displacement, and on x-axis we are plotting time. So vibration is represented by time displacement graph, and the graph can be of any general nature, can be of any shape. So in that case, the analysis becomes a little bit complicated. So what we do is normally decompose the components of the vibration into sine waves and cosine waves. Decompose components into sine or cosine functions. So this you know from your mathematics studies, that by use of Fourier transformation, any periodic curve can be represented as a summation of sine and cosine function. Can be represented by summation sine and cosine series. So hence, at the heart of any periodic function, so the basic condition for the vibration is that the time period should remain constant. The motion can be of any general shape, the vibration can be of any general shape, but time period should remain constant, and the phenomena should repeat itself. The phenomena should be periodic. So the wave should be of same shape over each time period interval, and the wave shape cannot change in subsequent time period interval. Otherwise, you have to define a different time interval. So if you identify a time interval that says that the phenomena is periodic, and the same displacement time graph repeats itself for the next time period. So for that, any such function by Fourier condition, we know that it can be represented by sine and cosine series. So hence, we will form our vibration analysis for the harmonic motion, that is sine and cosine series. So we will build up our basic theory on sine and cosine function, and then that can be applied to any general function by using Fourier transformation. This information you will not be using so much in your undergraduate studies, but later on when you are seeing real vibrations, you will be seeing the use of this property. So for now, we will analyze only sinusoidal wave profile. So we will lay down basic definition for a simple harmonic curve, a simple harmonic wave. A simple harmonic wave is nothing but a sine or cosine wave. So with respect to that, we will define some of our definition for a vibration. Let's say you are having a harmonic wave like this. The period of one wave is called a time period. So on the x-axis you have time, on the y-axis you have displacement that we usually denote by x, and the period of one wave, one cycle of the vibration to complete is called a time period. In the vibration literature, hardly you will find the use of defining vibration with the help of time period. Normally we use the term frequency. So how a frequency is defined? It is the number of oscillations or vibration cycles in 1 second of time. So 1 second of time. So if time period, let's say time period is t seconds, so one cycle takes t seconds. That is the definition of time period. So hence, how many cycles can be completed in 1 second? That will be equal to 1 by t. So 1 second divided by t seconds for each cycle. Let's say 0.05 seconds for each cycle. 1 divided by 0.05. So that you will get 20 as a frequency. So this is number of cycles in a second, and this is called frequency. So normally we will be dealing in terms of frequency in real system, where we come to realize the real system. So this is just a simple definition that f is equal to 1 by t, and f is measured in hertz. So the abbreviation for that is Hz. Another quantity which is related to a harmonic motion in particular is called angular frequency, or omega. So if you recall your mathematics derivations, you will understand that the sine wave can be generated by projection. Let's say this is a projection of a point moving about in circle. So if this is the angle theta, then this displacement x will be equal to r, that r is the radius of the circle, r sine theta. So hence the sinusoidal function can be found by projection of a point rotating in circle on y-axis. In circle on y-axis. So this is a property that we use in harmonic motion. Now, when the oscillation is such that it can be represented by sine wave, then it is called harmonic, and sine wave can be represented by motion of a point in circle. So this is a harmonic function. So a harmonic function can be generated by circle, and the complete angular rotation of the circle is 2 pi. So one cycle of harmonic function is equal to 2 pi, or 360-degree angle, 2 pi in radians. So that's so in reality we know that one cycle of oscillation takes place in t time period, t, that is time period that you define. So how do we find the relation between these two? So for that, a scaling factor is a ratio is defined as omega, that is angular frequency, that is defined as 2 pi by t. So 2 pi is in radians and time period is in seconds. So omega comes in radian per second. So if you want a physical interpretation, you can see this point moving in the circle. It will rotate at an angular velocity of omega, and the angular velocity omega in radian per second can be your angular frequency. So like this, you can convert your time domain into angular domain. So you can, instead of this will help in simplification of some expressions, some complicated expressions later on. So if you have the information in time units and you know the time period, you can do a conversion between frequency domain, a time domain, and the angular domain. So this helps in relating the time domain to angular displacement domain for simple harmonic, for harmonic motion. So that is the use. Like what is the relation between the angular frequency and the real frequency? So 1 by t you know is equal to f. So angular frequency is equal to 2 pi f. So this is the relation between angular frequency and f is the real frequency. Because we will be working with sinusoidal functions, if you use the 2 pi f and 2 pi by t, this kind of time, this kind of conventions, then it will be easier to evaluate the sinusoidal expression. We will get quantities like sine pi by 4, like that, and it will be easier to evaluate. So hence we are laying down this definition, and it gives an insight also that vibration is nothing but rotation of a point in a circle and position of that when we see on the y-axis. Another important definition for the harmonic curve is the amplitude of vibration. So amplitude of vibration is usually termed as x0, and that definition comes from the initial displacement. So if you have a spring mass system at its 0 rest position, mean position, you give it a x0 displacement from equilibrium, then it will oscillate between the positions x0 and minus x0. So between these two extreme position, it will keep on oscillating, and the mean position is 0. Similarly, this thing, if you put in the form of graph, if you this displacement you plot against time, you will get a sinusoidal wave, and this is the maximum displacement x0 for the positive side. Negative side also you will have maximum displacement x0. So x0 is called amplitude of vibration. So what is the significance of amplitude from the rotating vector method? That you have a circle and the position of circle on y-axis give you equation for displacement. So your maximum displacement will be here at theta is equal to 90 degrees. So this is some general data. So max displacement will be equal at will occur at theta is equal to 90 degree. In the simple harmonic graph also you saw that maximum will occur at pi by 2, that is 90 degree. So at 90 degree the displacement we saw that it is x0, the maximum displacement. Hence this distance from center, let's say O origin, to the maximum point P, OP will be equal to maximum displacement, and that is equal to x0. So hence this from the geometry is equal to x0. So the vector will be of the radius x0. So radius of vector x0, and the x0 will have for any given time theta displacement from the this is time, this is displacement. So at any time the vector of magnitude x0 will have theta degree angular displacement from the 0 degree position. So this theta degree is called phase of the vector, and x0 is amplitude of the vector. So this is called a rotating vector method. So from if you want to study two oscillations simultaneously, let's say one oscillation is this, another oscillation is this, third oscillation is this. So each oscillation can be represented by a vector is represented by vector in the circle diagram. So let's say this is vibration 1, oscillation 2, oscillation 3. So in the circle diagram they will look like, let's say this is vector 1, which is having some phase theta. Then here we will have vector 2, the magnitude may be different, something different. The phase will also be different, will have its own phase and magnitude. And let's say it will be the third vector 3. So all these three will rotate at their respective angular frequency, respective phase and respective vibration. But the interesting thing here is that if you want to calculate resultant two different oscillations, then you just need to add vectors using vectorial notation. So whatever you learned in the theory of vectors, how the vectors are added, that thing if you consider and get the resultant vector. So let's say this is vector 1, this is vector 2, and you want to calculate the resultant of those two. So we'll add these vectors and we'll get vectors somewhere like this. So principle of parallelogram, if you remember. So you'll get the resultant vector 1 plus 2, and this vector will represent the resultant both in magnitude and phase. So a complicated problem can be solved like this. If you have three different oscillations here, or two different oscillations here, that can become represented by vector space, and the vector can be added, subtracted, whatever you want, and then the resultant will give you the new wave. That is a combination of 1 plus 2. So this is called vectorial representation of vibration.